Structural constraints are the rules that tell data what it may and may not be. At their simplest, constraints define the allowed shapes, values, and relationships in a dataset so that stored information remains meaningful and reliable. Think of structural constraints as the grammar of your data. Grammar lets sentences be interpreted consistently. Constraints let systems and people reason about values with confidence. In this video, we will define structural constraints, examine the common types, show where and how they are enforced, discuss trade-offs and operational impacts, and finish with practical best practices you can apply today. First, what exactly are structural constraints? A structural constraint is any rule that restricts the structure or content of data. That includes rules about data types, required fields, value ranges, uniqueness, relationships between tables or records, and business-specific invariants. Constraints limit what can be stored or accepted, preventing invalid or ambiguous states. Why do constraints matter? Constraints protect correctness, enable predictable processing, and reduce downstream errors. When constraints are explicit, automation can validate input, queries can be optimized, and teams can share a clear contract about data meaning. Without constraints, small mistakes accumulate into costly bugs, incorrect analyses, and brittle integration points. Let's walk through the major classes of constraints you will encounter. First, type and format constraints. These are the foundation. Types restrict the class of values: integer, decimal, string, date, Boolean, and so on. Format constraints refine types with patterns or encodings, for example an ISO 8601 timestamp, an email address pattern, or a currency code. Type and format checks are cheap to evaluate and prevent many common errors. Second, nullability and required field constraints. A field may be required or optional. Required fields express that certain pieces of information must always be present. Explicit nullability prevents ambiguous missing values and forces teams to document what missing means in each context. Third, uniqueness and key constraints. Unique constraints and primary keys ensure that certain values are distinct across records, which is crucial for identity and deduplication. Primary keys give stable handles to entities. Unique constraints prevent duplicate business objects and enforce real-world uniqueness like tax IDs or invoice numbers. Fourth, referential integrity and foreign key constraints. These enforce relationships between records. A foreign key ensures that a reference points to an existing, valid parent. Referential integrity prevents orphaned records and keeps relational structures consistent across updates and deletions. Fifth, domain, range, and check constraints. Check constraints allow arbitrary predicates on values. A salary must be non-negative, a date must be after an employee's hire date, or a rating must be between 1 and 5. Domain constraints enumerate allowed values, for example a status column limited to pending, approved, or rejected. Sixth, cardinality and multiplicity constraints. These describe allowed counts in relationships, one-to-one, one-to-many, or limits on how many related items are permitted. They are essential for modeling business rules like an order must have at least one item, or a user may not have more than 3 active subscriptions. Seventh, temporal constraints. Time-related constraints include validity intervals, event ordering, and temporal consistency rules. Examples include ensuring a discount's end date is after its start date, or that a revision timestamp is monotonic. Eighth, composite and conditional constraints. These combine multiple fields or apply only under certain conditions. If payment method card, then card number must be present and pass a loon check. Conditional constraints capture richer business logic directly in the data model. Now, where are constraints enforced? Constraints can live in multiple layers. The most common places are the database schema, application code, ingestion pipelines, and validation services or gateways. Database-level constraints are powerful because they are centralized and enforced by the storage engine. Relational databases provide native support for many constraint types, nullability, primary/foreign keys, unique constraints, and check constraints. This makes the database a strong last line of defense. Application-level validation is more flexible. Applications can implement complex semantic checks, cross-entity validations, and human-friendly error messages. But constraints only enforced in application logic risk inconsistency when multiple services or bulk loaders bypass that logic. Ingestion and pipeline validation are critical when data flows from external sources or event streams. Schema registries, validation libraries, and streaming filters can reject or quarantine bad messages before they enter core systems. Validation as a service and contract-driven design are useful patterns in distributed architectures. They make constraints discoverable and reusable by multiple clients. What about trade-offs and operational impacts? Constraints improve correctness, but introduce friction. Strict constraints may reject incoming data that is late, malformed, or from a new version of a producer, requiring coordination. Conversely, lax constraints increase downstream risk, silent corruption, inconsistent analytics, and subtle bugs. Performance is another consideration. Some constraints are inexpensive to check. Others, like cross-table invariance or expensive computed checks, can slow writes or require careful indexing or background reconciliation. Schema evolution complicates constraints. Adding a non-naiadable column, tightening a check, or changing a type are breaking changes if consumers are not prepared. Migrations must be designed to be back-compatible. Introduce new nullable columns first, backfill data, then enforce stricter rules. A practical approach is to adopt a layered validation strategy. Reject obviously invalid or malicious input at the edge. Validate and normalize at ingestion. Enforce critical invariance in the data store, and run background reconciliation jobs for weaker or expensive checks. Monitoring and observability are essential. Track validation error rates, rejected message counts, and schema change events. Logging and metrics help you detect drift, broken integrations, and data quality regressions before they become business problems. Testing constraints is also important. Unit tests for constraints, integration tests for migration paths, and property-based tests for invariance will catch edge cases early. Include constraint checks in CI pipelines and validate schema compatibility as part of deployment. Governance and documentation complete the picture. Maintain a schema registry or catalog with explicit constraint definitions, examples, and rationale. Document what missing means for each field, which units are used, and which checks are critical for business correctness versus those that are advisory. Let's look at a few concrete examples. Example 1. A payments table. Constraints: payment ID as primary key, amount as non-negative decimal, currency as a 3-letter ISO code, status constrained to an enum, and a foreign key to orders. These constraints prevent invalid currency codes, negative amounts, and orphaned payments. Example 2. A user profile ingesting external data. At the ingestion layer, apply format checks for emails, require a stable external ID, and mark records with unknown or missing critical fields for review rather than immediate rejection. In the database, enforce unique constraint on email or canonical identifiers and validate normal forms for contact info. Example 3. Time series telemetry. Enforce monotonic timestamps per device, range checks for plausible sensor values, and cardinality limits on dimension cardinality to avoid unbounded growth. Finally, best practices you can apply immediately. 1. Codify constraints where they are most enforceable. Put simple, universal rules in the database and complex semantic checks in the application with shared libraries. 2. Make constraints discoverable. Publish schemas and validation rules in a registry or API contract. 3. Favor additive, backward-compatible schema changes and automate migrations with staged rollouts. 4. Instrument validation outcomes and treat rising error rates as a first-class alert. 5. Keep a recovery pathway, quarantine, reconcile, and human-in-the-loop repair for cases where automated recovery is unsafe. In summary, structural constraints are the essential rules that keep data meaningful, reliable, and maintainable. They are a balance between protection and flexibility, and when designed and enforced thoughtfully, they sharply reduce risk and increase velocity. Design constraints explicitly, enforce them consistently, monitor their effects, and evolve them with care, and your data will remain an asset rather than a liability.